Hello, and welcome back to Introduction to Astronomy. And so far, we've been talking about things that are moving in a straight line. So we talked about distance in a straight line. We talked about speed in a straight line. We talked about acceleration in a straight line. We talked about force in a straight line. We talked about momentum in a straight line. But you should remember that in the universe, things are not only moving in straight lines, they're also spinning. So we would like to be able to describe objects that are spinning. And here is an object that spins. So this is my wheel here, and you can see that I can spin the wheel. And so in the same way that we had distance that was sideways, we could measure something that's rotating by the angle that it goes through. Okay, so you see this thing is straight up and down, and I could move it through 90 degrees. So the angle through which something rotates is equivalent to the distance that something moves sideways. Do you think that there's something equivalent to linear speed in meters per second? Yeah. So it's called rotational speed. Now, unfortunately, they've got weird letters that represents all of this. So that rotational speed is given by the letter omega. So I know that looks like a W, but it's a Greek letter W, which is called omega. And that's what rotational speed is symbolized by. And the official metric unit for rotational speed is going to be called a radian per second, which we don't care about. Okay, I'm just going to go with something that you're more familiar with, RPMs. So what does the letters RPM stand for? Rotations per minute. So if something is rotating at 1 RPM, then it will go completely around one rotation in 1 minute. Okay, if it's going at 10 RPMs, then it will go around 10 times in 1 minute. So there's a formula that goes with rotational speed, like there is a formula that goes with linear speed, but we're not concerned with it. I just want you to know, what do I mean when I say that something has a rotational speed? There's also rotational acceleration. And just like linear acceleration was the letter A, rotational acceleration is the letter A, but it's a Greek letter A. And so it's alpha. So that's what that funny looking letter there is. So that's an alpha. And so a rotational acceleration would do what? It would cause the rotational speed to change, just like a linear acceleration causes linear speed to change. So an example of this would be a top. So there you've got a top there, and there's a string wrapped around it, and then what you do is you pull on the string, and then it makes the top go around and around. So before you pull the string, how fast is the top rotating? 0, okay? So it starts at 0, and then as you pull it, it's going faster and faster. So its speed is changing. So that would be an example of a rotational acceleration. So, and there's formulas that go with that, but it's not important that you know. Just understand, what do I mean? To spin, I had to put my hand on it, and I had to move my hand. So I was applying a force. So my force was in this direction, and then when I apply it, it causes it to turn. But there's something else involved, and that was the radius. So did you notice that I applied my force up here a certain distance away from the axis? So that's going to be the letter R. Radius is going to be the letter R. F is the force that I'm applying. So when you multiply those two things together, that's called a torque. And it's given by the letter T, but again, it's a Greek letter T. So it kind of looks like a T, but it's the Greek letter T for torque. And a torque is a twist. So think about a ketchup bottle. If you've got a ketchup bottle and you're trying to get the lid off of it, you need to apply a twist to it. So you're really applying a torque to it. Now, if, on the other hand, let's say that you've got a nut and you're trying to get that is only about this big on that nut. So what do? You get a wrench. So what good does a wrench do? The wrench has a long handle, so it's a larger radius. So that means you don't need to apply as much force in order to twist the nut off. Okay, so torque depends on the amount of force you apply and where do you apply it. Okay, so that's what I mean by torque. And torque is going to be the thing that causes things to rotate. Okay, here is yet another concept for things that are rotating. In general, things that are rotating is more complicated than things that are moving in a straight line. So do you remember when things were moving in a straight line, we talked about mass, and we said that the more massive the object, the harder it would be to get it going, and the harder it would be to stop it from moving. So when you've got a wheel, there are properties of the wheel that either make it really easy to spin or very hard to spin. And that's going to be called the moment of inertia. And there is a formula for it, but I don't want you to know it. I just want you to see, what does it depend on? Well, one thing is the heavier the wheel, the harder it's going to be to spin. So it depends on the mass of the wheel. Okay? Another thing would be the size of the wheel. So if you had a big wheel, so a wheel that had a radius that came all the way out to here, it would be harder to spin it than if you had just a little tiny wheel. You could do that with your fingers. Okay? Another thing it depends on is where is the mass located at. This is really cool. So you see those two objects there? One of them's a ring, and then the other one's a disc. And they're both the same mass, and they're both the same radius. And so you can take those two objects, the ring and the disc, and put them on a ramp, and you let them go, and one of them will get down to the bottom of the ramp before the other one will, because it not only depends on the mass, but where's the mass located at. So do you notice that on the ring, the mass is located on the outside of the ring, whereas in the disc, the mass is uniformly in there. Now, I'll show you how you could figure out which one would get to the bottom of the ramp here in just a moment. And then the last one is, it also depends on how you rotate it. Okay, so for this one, what I recommend that you do is you get like a pipe, okay, for this little demonstration. Let me put this down. And you could take the pipe, and it's better if the pipe is long, but you could take the pipe and do this with it. Okay, then I want you to take the pipe and I want you to do this with it. And then I want you to take the pipe and I want you to do this with it. You see I'm turning it? And what you're going to find out is there's a difference between trying to turn something like this, trying to turn something like this, and then trying to turn something like this. So all of these factors go together to make a constant. And that constant is called the moment of inertia, I. And in physics, if you take a physics class, you would learn how to actually compute what that moment of inertia is. But all I want you to know is that the moment of inertia is to rotating systems what regular old mass is to objects that are moving sideways. Okay? So let's take another break. If you haven't done so already, you might want to get something to eat, okay? And then when you come back, we'll continue with this.